Okay. So, Bismillahir-Rahmanir-Rahim. So today we're going to discuss the classful subnetting. As we said, that chronologically, classful subnetting and classful routing was actually designed or was established in the internet before the classless. And classful talks about the fact that we don't have to have the subnet mask accompanying the IP address every time we send an IP address. So the subnet mask is going to be inferred or extracted or guessed just from the address itself. So basically, what we need to do is to focus on the leftmost octet. So if that octet is in a specific range, then we know that this is class A. And based on that, based on the class, we can right away figure out what the subnet mask is. So class A talks about the fact that the first left octet is going to be the network part, which means that the host part is going to be 0.0.0. Okay, and here is going to have a specific number. So any class A will have this as a specific number in a specific range, and the host part is going to be 0.0.0. Class B will have two octets as the network part, and two other octets as the host part. Class C is going to have three octets as the network part and one octet for the host part. Which means that basically class A, for any class A network, you can have up to 2 to the power 24 hosts. 2 to the power 24 minus 2. And here 2 to the power 16 minus 2. And here 2 to the power 8 minus 2. Okay. Class D is for, as we will see later, is for multicast. And in that case, all the 4 bytes are for hosts, and again it's in a specific range. So if the first byte is in a specific range, then we know that this is a class D or multicast address, and in that case the whole address is going to be a host part. There is no network part and host part. For multicast, it has a special way of routing which does not actually depend on any subnet mask. So it's a direct routing. You don't have to divide the address into host and network. So in the early days of the internet, the IANA or the organization that is responsible for assigning the IP address, they actually came up with this as a publication. They said that we're going to classify you as one of the address classes A, B, C, or D, depending on the size of the organization and depending on whether you're tier 1 or tier 2 or tier 3 and so on. So later on, of course, as we all know, the CIDR, or the classless inter-domain routing protocol, has been proposed by IETF to mitigate the issue of coarse or the discriminant classes of the IP address, which, as we will see in a minute, limits the granularity of the IP address in terms of how you divide it. So these are the classes. So in class A, we have, these are the network part and the host part. The network part is what we call is assigned by what we call the ARIN, or the American Registry for Internet Numbers, and this ARIN, they came up with the ranges of the first octet, which indicates whether this is class A or B or C or D. Okay, and there is the host number, which is assigned by the administrator. The administrator of the network is the one that, that says, within a Class A network, we need to have this host is assigned this host address and so on. So Class A ranges from 0 all the way to 127 in this octet. So any network that takes the number from 0 to 127, so from 0 to 127, this indicates Class A. So 9 dot something is class A, 126 dot something is Class A, and so on. 127 dot something is Class A. And that's why the loopback address is 127.0.0.0 or dot anything in the rightmost three hosts, because that was actually proposed or was well known in the classful routing days. So in that case, once we find that the leftmost byte having a number in this range, then we know that the host part is composed of 3 bytes, and that means that the number of hosts we can host on this network is 2 to the power 24 minus 2, which is this 16 million hosts. As you can see, you have 127 networks all over the world, okay, which is a very few number compared to, of course, the how large the internet is. And each of these networks, they would have huge amount of hosts. Of course, this is a coarse way, a very discriminative way of dividing the IP address. But of course, in the early days, this was okay because the internet was not as we see it today, of course. So that was okay in the early days. So 24 dot something is Class A, 63 dot something is Class A, and so on. So Class A addresses account for 2 billion. Where this 2 billion came from? Where do you think this number came from? 2A? What?
Because it says it's number of possible IP address version 4. So is it greater than version 4?
No. And I'm saying, how do we get this number? How many networks do we have in Class A?
2 power 127.
Hmm?
2 power 128.
2 to the power 128? This is huge.
Because we have 128 networks in Class A.
128 بالضبط أيوة.
Yes.
أيوة, each one has
Each one has 24.
أيوة. One يبقى so we have one. So this number came from the fact that we have 128
Times 24.
networks in Class A. Each one has how many hosts? 2 to the power 24 hosts. So this accounts for this number. Okay? So when you do this multiplication, this is this number. Of course, there's minus 2 in the host. Okay? So this actually is 50% of all the IP addresses, all the IP address domains. So if you calculate this number, and if you calculate the number, how many possible addresses we have in all classes? 2 to the power 32, right? These are all the addresses. All the IP address domain is 2 to the power 32. 32 is the number of bits that we have, right? So this number turns out to be 50% of this. 2 to the power 31. So we have 2 to the power 31 addresses only in Class A. Okay? This is a huge number, of course. So we have in class B, we have from 128 all the way to 192. 128 all the way to 192. This is the range of the networks in class B. If the range of the address is in that range, the range of this byte is in that range, then this network is also, or this byte is also part of the network address. Okay? So each of these networks will have 2 to the power 16 different hosts. Okay? So how many networks do we have here? If you try to account for this number, you will find that the number of addresses in class B is 2 to the power 14 times 2 to the power 16, okay, which is around 25% of all the IP address domain. So 50% is class A and 25% is class B. And we'll see how this number came from. Okay? So next is class C. Class C is from 192 all the way to 223. If you remember, 192 is a, remember 192 is 11 all zeros, right? And 223, the number next to it is 224, which is a 111 all zeros, right? So and of course 127 is 1 all zeros, right? 128, yeah, is one from 0 all the way to 127. So the next number is 128, which is 1 all zeros. So if this is 1 and anything else is changing, this is class A, which gives you 50%. If you remove 2 digits, okay, and change anything else, this accounts for 25%, which is the whole address domain divided by 2 divided by 2. Okay? If you account for this range is divided by 8. Okay? So which is 25% divided by 2, which is 12.5%. So the class C, that's why class C has 12.5% of all the possible IP addresses. Okay? So if the first left byte is in this range, this indicates class C. If that's the case, then you have how many networks? You have all these 3 bytes as networks. So you have a huge number of networks. Each one of them has very few number of hosts. Okay? So how many networks do we have? So 192 is 1 and then you change any of this, right? If you change any number here and you change all these numbers, how many bits do we have for the network part? 24 minus 2 bits, so 22. So this number is 2 to the power 22 networks. So we have 2 to the power 22 networks in class C. Each one has 2 to the power 8 hosts. Okay? So in total we have 2 to the power 30, 2 to the power 30 different addresses in class C. Okay? Which is around 12.5% of all the address domains in the internet.
So Dr. Again,
power 20, so we deleted 2.
Yes.
We took off 2, so it's 2 to the power 22 or 2 to the power 20.
2 to the power 22.
Okay, so this is the number of
Networks.
And then we have the total number of different IP addresses is 2 to the power 30.
30, right, because you have 2 to the power 8 hosts.
Yeah.
Okay, so in total it becomes 2 to the power 30 hosts.
No, why 30? Because
8
8
plus
plus
24.
22.
8 plus
Okay. So if you go back, so the network portion of the IP address was dependent upon the first octet, and there was no base network mask. So there is no subnet mask associated with any classful address in that case. So from the first byte, we already know or we can assume the mask based on that, because we can divide the network part and the host part without having to have the subnet mask. Okay. So for class A, we need to know that the number 128 is reserved. So there are some addresses, some specific addresses that are reserved. For class D accounts for anything that's 1110. I have to say something here. I think the 192 to 223. This number is 110 and something. Okay.
Okay.
110 and then anything. Okay, so you have to have 0 here.
Okay, once it's 1, so it's
Yeah.
class D.
Yes. So once this is 1 and this is 0, this is class D in that case. So 1110 is class D. So if we go back to this, so hopefully nothing is. Okay, so for class D, you have 1110 and then anything else. Right? So you know how many, you can calculate how many. طبعا in class D, there's no network and host part, right? So everything is host. So how many host addresses you have? 32 minus 4 is 2 to the power 28 different hosts allocated for class D, right? We have class E as well. Class E is anything else 1111 and then anything else, right? So class E addresses are reserved for experimental purposes. These are, again, D and E, we're not gonna use them that much, right? So we are going to use A, B, and C classes a lot. So that's in brief. So in general, so this particular example, so what is the class of this address?
B. Z. B. C.
Here, this is on the boundary, as we said. Yeah, so starting from 192 is C,
Yes.
right? So this is class C, which means that the default mask is what?
255.255.00.
And then 255. Yeah, 255.255.0, right? So this is C. In other words, this is /24. Let's say this is /24, right? And in that case, what is the network address?
192.168.00.
192, 168.1.0. Okay, and the subnet, the broadcast is
We have it
255 here, right? And then the host will range from this is 1 and this is 222.54, and that's it, right? So 1, this is A, واضحة طبعا, the class A, which means that أنا كتبت C. Okay, so this is class A. The default mask in that case is 255 dot all zeros, right? The network part is 1 dot all zeros. here is 1.255.255.255, and the host will range from 1.0.0.1 all the way to 1.255.255 to 254, right? So 172, this is a B, and so on. And you can do that. Okay, so that's this is the so class A. So in that case, this is like a brief summary of this. So class A, it has the first bit 0. It has to have 0, the first bit, and then anything else. So from 0 all the way to 127, because 128 will have 1 here, and this is not part of class A. And in that case, the network part is 8 bits, the host part is 24 bits. And B, you have 10 something, okay? So it ranges from 128 all the way to 192, because 191, sorry, because 192 is 11. And then you have 16 bits and 16 bits. C is 110 and then anything else. D is 1110 and then anything else. And then E is 4 ones. Okay? So that summarizes all the classes. So this is a pie chart of the percentages of the IPs in each class. So we have we have class A, 50%, class B is 25%, class C and class D, each one, class D and E, of course, they share this 12.5%. So each one of them, actually class D takes the biggest percentage, and then class E takes a smaller percentage. But we don't care يعني, so much about D and E, as I said before. C has 12.5%, and remember the way this is classified now is that very few networks, they have 50% of all the IP addresses, whereas huge number of networks, they have very, very small percentage of the IP address. So this actually advocates discrimination. So when they came up with this classful IP addressing, they were really emphasizing discrimination. So we do discriminate. Some organizations in of course mostly in the US, 128 networks only. I remember I used to work in IBM in North America, and they used to have address starting with 9 dot something. It's a clear discrimination. So you have very few organizations all over the world with class A, which means that they are allowed to have 2 to the power 24 different hosts in their network. Of course, big organizations only would have this, and then all the other, poor guys, they have to contend on class C addresses, which are very, very few.
Okay. So for the classless, the first octet is still the same, like numbers and ranges, but we only.
No, I have to tell you whether this is classful or classless. You have to have, because the routers themselves, you have to say classless or classful.
But now we understand the first octet for the classful. So the first octet for the classless, and how we can know why it's, for example, 190.
As I said, no. You have before you start talking about how you divide the IP, I have to tell you beforehand whether this is classful addressing or classless addressing.
Okay.
If I tell you this is classful, then you use the rule of classful by checking the leftmost octet, and then you figure out the class. Based on that, you divide the address. If I didn't tell you anything, then it's classful, which is the default mode of all the routers that we have nowadays, unless you explicitly tell the router word classful. Okay? Most of the routing protocols, they use CIDR, or they use classless inter-domain routing protocol. So unless the administrator manually comes to the router and say classful. So one of the very, very few routing protocols that work on classful is RIP, Routing Information Protocol. This is one of the earliest routing protocols that does not know anything about classless routing. Although even حتى in recent versions of RIP, they use classless routing. So RIP version, I think version 2 or something, it uses classful, whereas version 3, it uses classless. When all the routing protocols that uses classless, they by default use classful as well, but you have to start them. So the thing is, RIP version 2 by default works classful, and it assumes all the addresses are without subnet mask. So this is the default mode because it doesn't know anything else. But all the newer versions of routing, like RIP version 3 or EIGRP or OSPF or all these routing protocols, they are by default classless unless you have to force it to work on classful, which is very rare to happen. I'm not aware of any single organization that uses purely classful routing anymore. Okay. But of course, the addresses are being preserved since the early days based on 9. something. So IBM used to be in class A, but now it's not anymore. So everybody uses classless routing. In case you have to use subnet mask together with the IP address. So in any exercise or any problem, I have to tell you beforehand whether this is classful or classless, right? So that you can. So if I give you an IP address and then I say classless, I don't have to give you subnet mask.
You mean classful?
Classful. Yes, classful. If I give you an IP address and then I don't give you a subnet mask, then you assume that this is a classful. So of course, because of the shortage of IP address, which we have been talking about in chapter 5 and chapter 6, the shortage of IP address is clear. Some people have tried to work around this by saying, okay, so we have CIDR, so we can work around this shortage. Okay, so CIDR kept IP version 4 surviving for many years, for some years. But then we still have some shortage, even after using CIDR. So we came up with NAT, or we came up with the fact that, okay, so we can reuse some of these IP addresses and allocate some private IP addresses and public IP addresses. So we allow the home networks, the small home networks, to reuse addresses in certain ranges. Well, so this was smart, very simple idea. But then we have to do something in the router, of course. The router has to support NAT and PAT. So that also, solved the problem to some extent. So right now we can reuse addresses in certain ranges, and we can use NAT and PAT in the routers. So that's all fine. But that's not going to again solve the problem on the long run. So while people have been trying to keep the IP address version 4 surviving using some what we call evolutionary approaches, like some incremental contribution or some incremental things that can work around the fact that we have shortage in IP address version 4, some other people took the revolutionary approach. They said, just let's forget about IP version 4 altogether. We know that the shortage problem is going to be clear, and we have to face it at some point, if not today, tomorrow. And nowadays, especially nowadays, it's becoming more and more serious and more pressing that we need to migrate everything to IP version 6. So IP version 6 talks about the fact that we have shortage in IP version 4 because of the fact that we have 32. We did all what we can to to stay with the 32 bits address, but that solves the problem incrementally, not fundamentally. So we need to plan for the future. So the first thing they did is that they said, okay, the address is going to be 128. So the number of IP addresses you cannot even pronounce. We cannot even know what this number looks like. So these are the possible addresses using 128 addresses. Okay. So this is, of course, this is going to increase the size of the IP header and so on and so forth. But that's not the problem. The problem is that you have to change all the routers on the internet to use IPv6, which is not that easy. You're not just changing a flag field in the IP header, and then if you check this flag field, you will do something. If you don't check it, you will not do this, but you will not affect the overall functionality of IP. Here, this is a fundamental change. It's going to change the whole protocol from scratch. So that's why the adoption of IPv6 has been very slow. Why? Because in order for you to use IPv6, everybody has to work on IPv6. All the routers have to be IPv6. Okay? So we cannot do that in one night. I mean, it's a fundamental change. So some people, they have proposed to do like incremental change of a certain network. Okay, so in smaller network you can use IPv6 in a small network, but then when you go out, like the default gateway has to map from IPv6 to IPv4 before you go to the internet. Because if you send a packet with IPv6 to Ooredoo, they will tell you, we don't understand what this is. Okay, so maybe Ooredoo, inside their infrastructure, they have some smaller network which can again work in IPv6, but again, when they send something out. So the idea is that in order for us to work on IPv6, everybody has to work on IPv6. So the adoption of IPv6 has been very slow because of the fact that it's a fundamental change and it requires to change the whole infrastructure. So we cannot afford this. So what we could do is that we change small networks, okay? We change the infrastructure in smaller networks gradually until we reach to a day that hopefully within a few years that we can say, okay, the whole infrastructure from tier 1 all the way to tier 3 is all IPv6. So in that case, we will have the complete freedom of IP addresses, and we will not have the shortage of IP.
The changing is bottom to top or top to bottom?
It,
bottom to top, right?
well, it depends how you define top and bottom.
I mean,
So
top is the tier 1, right?
right.
So I mean, you're changing in the very small, which is tier 3.
We cannot say it's top down or bottom up because, as I said, tier 1 or tier 2 or tier 3, they have a complete freedom to change their network inside, their small network inside. But in terms of communication with the outside world, it's still IPv4. Okay? Because if we change it, then the other side will have to change. So within a service provider, inside there is small parts that can work IPv6, but when you go out, it has to be version 4. So there are some gateways that they worked on that it kind of maps from 6 to 4 and from 4 to 6. So these gateways are the entry point to the internet or back to the entire network. So that's why, despite the fact that IPv6 seems to be very attractive in terms of the address domain and everything, but still some people, they anticipate IPv4 to survive at least in the next 10 years. because it's still the predominant protocol in the internet. So, so there are people have been working on some proposals to do like gradual deployment of IP version 6 in certain environments, but again, the wide-scale deployment of IP version 6 is not going to happen in 10 years or so. So the لو سمحت لو عايزين تتكلموا كده ممكن تطلعوا برا. We're not forcing anyone to attend. So in terms of short-term solutions, as we said, we have 4 different solutions as incremental solutions. So we worked on CIDR, and CIDR seems to solve the problem incrementally. We worked on VLSM, which helped us to be more flexible in terms of dividing the addresses recursively depending on the demand and the requirement of each network. So we're not forced to divide the IP address horizontally by saying we are allowed to divide it once and the sizes of the subnets have to be the same. No, VLSM allows you to have variable length subnet mask, and that also gave us some flexibility. And then by defining the private addressing and NAT and PAT, we were able to reuse some of these. So all of these are, again, evolutionary or incremental solutions that have kept IP version 4 surviving for quite some time. And it's still going to survive in the next probably 10 years or so. So this is IP version 6. And in IP version 6, as we can see here, the IP address itself spans 32 times 4, 128 bits for the source address and the destination address. So the IP version 6 as well tries to solve some of the problems of IP version 4 fundamentally. Like one problem is quality of service. So quality of service has also been one of the problems of IP version 4. So IP version 6 tries to again solve that. So if you remember, IP version 4 gives very rough way of quality of service. So you can give some special quality of service for video versus audio versus, but you cannot give quality of service based on certain session end to end. You don't have, because IP is connectionless, right? So you don't have the context of a session, of end-to-end session. So I need to, for example, give a specific quality of service for that user or for this session or for this application, right? Regardless of whether this is video or audio or what. So I need to be able to have, flexibility and more control. And that was not done by IP version 4. So also IP version 6 tries to solve that. We'll talk about this in details next time, inshallah.